Hi, my name's Will Krawczyk, Scientific Services Manager at Chemical Computing Group. Today I'd like to show you surfaces and maps. Surfaces and maps can be accessed directly from the right-hand side button bar in the main window. This application can be used for different systems ranging from small molecules to proteins, including peptides, antibodies and other macromolecules such as DNA or RNA. There are three parts to the panel. The first will list the different surfaces. The middle section allows for creating different surfaces and hotspots as well as loading electron density files. And the third section allows to control rendering and style. Today I'll be showing you three different examples starting with the protein-ligand complex. Bear in mind that each surface can be applied to any modality. In each example the structure has been prepared using Quick Prep. Before I hit create I have options to modify the colour, material, the rendering style, as well as overlay the H-bond information, which is useful for structure-based drug design. I'm going to start by generating an interaction surface using the default settings, and this is going to generate an interpretable surface to help understand steric availability. For better visualization, I'm just going to toggle to mesh rendering. This provides a zero potential contour of the van der Waals potential of a probe atom with the molecule. Where I see the heavy atoms of the molecule touching the edge of the grid, this tells us the ligand has an optimal steric fit. If I was to see the ligand protruding beyond that surface, it would indicate a clash. That's not the case here, but conversely, where I see a gap between the ligand and the surface, this tells me we have an opportunity. It's an opportunity to optimize the ligand by placing atoms on this surface. I'm just going to hide the surface so we can come back to it later. In our next example we'll be using an antibody, so I'll just toggle to that system using the System Manager, and here I'll be generating a molecular surface, also known as a Connolly surface. With the current settings I'm going to be creating a surface around the receptor atoms in the vicinity of the ligand atoms. This is useful when I want to visualize a binding pocket. However, in this case I don't have a ligand present. I do, however, have options to select sets of atoms that were created during the preparation of this molecule when I annotated it. So for example, I could focus in on a specific CDR region if I wish. Today though, I'll change the near setting to be receptor atoms, and I'm going to color by lipophilicity and change the rendering style to solid. This will allow me to identify the greasy hydrophobic regions of the surface shown in green relative to the polar regions which are shown in purple. I can display more than one surface at a time, so for example I could use protein patches to allow me to identify regions of excess hydrophobicity or charge. For better visualization I'm just going to hide the molecular surface. And when I do so, I can see here that we've got the excess hydrophobicity regions shown in green, excess positive charge is shown in blue, excess negative charge shown in red. Protein patches can be useful to assess potential developability issues. For example, a large hydrophobic region such as this, especially in the presence of the CDR region, could be a source of aggregation or self-association. Charged regions such as this can present issues with respect to viscosity. I also have direct access to the patch analyzer for easy analysis of these patches. This provides a list of the patches in the system in order of size, together with options to visualize and identify the residues that give rise to these patches. This is all covered in a separate video, so I won't go into detail here. Our next example is applied to RNA, so I'm just going to use the System Manager to toggle to that system. And in this case what I'll be doing is generating an electrostatic map so that we can generate electrostatically preferred locations of hydrophobic, H-bond acceptors and H-bond donors. This is providing information on the receptor, not the ligand. It tells us where the receptor would like to see an interaction, and it tells us what type of interaction the receptor is looking for. This is all useful information for structure-based drug design and improving ligand design. In the main mode window I see white, red and blue hotspots corresponding to the hydrophobic, acceptor and donor hotspots. Let's go through these one at a time, starting with our hydrophobic hotspots. Here I can see that the ligand, the aromatic features of the ligand are touching the hotspots. This tells us the ligand is already well optimized for hydrophobic interactions. Let's move on to look at our acceptor hotspots. Here I see two hotspots originating from the magnesiums. In this case, the ligand is not satisfying the hotspot in the sense it's not touching. This, however, presents an opportunity to modify the ligand so that we could pick up an interaction with one of these hotspots. Finally, I'll toggle to the blue donor hotspots, and here I can use the energy slider to display different energy levels in kilocalories per mole. In this case, we find the ligand is anchored by these donor interactions, but there are potential opportunities to improve the design of our ligand to take advantage of one of the acceptor interactions that we saw. In our final example, I'll show how we can use surfaces for comparing binding pockets or identifying structurally conserved regions. For this, I'm going to load in the same EGFR receptor as we saw in the first example. The first example was using 1M17, which had a ligand called erlotinib bound, whereas 1XKK has a ligand called apatinib bound. I'm going to generate an interaction surface as we did before in that first example, and I'm going to set the line view to the rendering style to be line. I'll just bring back the complex from that first example, 1M17, select both of the surfaces, one hidden, one shown, and then I can use the toggle button to toggle between the two. When I do so, I can see that the second complex has a sub-pocket which we would not have known from looking at the 1M17 structure alone. I'm just going to delete both of those surfaces and just quickly mention that we can use the S button in the System Manager to generate or modify surfaces, which is useful when we have multiple surfaces in our system. Also, the commonly used surfaces are accessible from the right-hand side button bar. In this case, when I've got two complexes active in the main Mo window and I hit Interaction Surface, Mo will create an interaction surface for each of the complexes in the Mo system. In this case, one for 1M17 and one for 1XKK in just one click. And that brings us to the end of today's session, where we use surfaces and maps to analyze the surface properties of a series of different molecules, small and large. Not covered in today's session, the Surfaces and Maps panel can also be used to display contact preference, interaction potential, external grid files, and electron density surfaces. If you have any questions, please do reach out to us at support@chemcomp.com.